Hello, this is Math 2115 coming to you from the College of DuPage during the fall of 2020. And this is the conclusion of the lecture on set theory. Last time I left you with this problem to do. I hope you did it, but if you didn't have time, I'll give you some more time to do it. You know what to do. Let's see how you did. The answer should be the first one is not true because the third element is 3 here and is 4 here. They're not the same 4 tuple. Number B, they are the same because the numbers are equal. 1/2 is actually equal to 3/6 minus 2 whole squared is 4, and the principal square root of 9 is 3. Another notation, which is important in both mathematics and in computer science, denotes objects that are called strings. Here's a definition of a string. Let n be a positive integer. Given a finite set A, a string of length n over A is an ordered n-tuple of elements of A written without parentheses or commas. The elements of A are called the characters of the string. The null string over A is defined to be the string with no characters and is often denoted by the Greek letter lambda, and it's said to have length 0. If A is equal to the numbers 0 and 1, then the string over A is called a bit string because these are binary digits 0 and 1. Here's a problem dealing with strings. Let capital A equal the set A comma B. List all the strings of length 3 over A with at least 2 characters that are the same. You know what to do. Let's see how you did. So these are the, let's see, 1, 2, 3, 4, 8 strings that are possible. In computer programming, it is important to distinguish among different kinds of data structures and to respect the notations that is used for them. Similarly, in mathematics, it is important to distinguish among, say, the set containing A, B, C, the set containing the set of A, B, comma, C, the ordered triple A, B, C, the ordered pair A, comma, ordered pair BC, comma, ABC, and so forth. These are all significantly different objects. Venn diagrams, named after John Venn, provide pictorial views of sets. And so, for example, you could say that all the universal set is inside this rectangle. A can intersect with B, and since you either can be in A or not in A, or in B and not in B independently, there are 2 states of nature times 2 states of nature, and so there are 4 regions that are shown here. The region 1 is outside of A and B, or it's outside of A union B. Region 2 is in A, but not in B, is A minus B. 3 is A intersect B. 2, 3, 4 is A union B. And 1, 2, 3, 4 is the universal set. Now here we're just talking about these being regions. We can also do colorations of descriptions. So on the left-hand side you see A union B, and on the right-hand side you see a Venn diagram representing A minus B. Here's a kind of problem that you often would run into. Among a group of 165 students, 8 are taking calculus, psychology, and computer science. 33 are taking calculus and computer science. 20 are taking calculus and psychology. 24 are taking psychology and computer science. 79 are taking calculus. 83 are taking psychology. And 63 are taking computer science. How many are taking none of the 3 subjects? So this is a type problem I could ask. I often ask this kind of problem on a test. I should have put this symbol here, but let's see how you did. This is what you should have come up with, and the answer to the question is 8. Now some of you might be saying, boy, I wish there were more of these, or I wish we talked more about it. Well, this is a rare instance, because I usually don't, but this is an example I took out of the reading in your textbook. So there's a detailed explanation of how to get here. And you might be saying, boy, I wish I had another one to practice. Well, you do. You have a whole bunch of practice exercise problems that are there, and some of them deal with exactly this kind of problem. We call a set script S, whose elements are sets, a collection of sets, or a family of sets. And so, for example, and we talked a little bit about this before, but if script S is equal to the set containing 1, 2, and then the set containing 1, 3, and then the set containing 1, 7, 3, there are 3 things in S, but it's a collection of 3 sets, so it consists of those 3 sets. We say its sets X and Y are disjoint if they don't have anything in common, if their intersection is null. And a collection of sets, S, script S, is said to be pairwise disjoint if whenever you take any 2 different sets in S, they're both disjoint. We do also have the first theorem of our course quoted in this, and these are things that are true about sets. Both union and intersection are distributive. The groupings can happen this way. They're also commutative. It doesn't matter in which order you do them. Intersection distributes over union, and union distributes over intersection. Whereas if you add 0 to a number, you get the number back again, and if you multiply a number by 1, you get the number back again. The same thing is true with sets. We have identities for the union and an identity for the intersection. We have complements. Something is either in A or it's not in A, and together it adds up to the universal set. Something's never in A and not A, and therefore that's equal to the null set. And we have different things. I'm not going to ask you to remember the terminology here, but you should remember these results. Down here, the complement of the complement is the set itself. The complement of the null set is the universal set. The complement of the universal set is the null set. And we have De Morgan's laws for sets. The complement of the union is the intersection of the complements. The complement of the intersection is the union of the complements. We prove these things when we get around to proving theorems by taking, let's just start down here with De Morgan's law. We show that this side is a subset of this side, and then we in turn have to also show that this side is a subset of this side. A lot more about this later. You might also notice that these properties, in particular De Morgan's law, bear significant kinship with what we saw in logic. More about that later. In closing, then, now, more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. God bless you all.